This lesson is on inequalities, and we're going to talk about how to graph them and what symbols go with which inequalities. So first of all, we use an open point for strictly less than or greater than signs. So for example, number 1 and number 2, you would have open points on the boundary, which is 3 on number 1, and it says x is less than 3. Well, if you notice, the less than sign fits on the arrow going to the left. And if you also know, going to the left is where the numbers keep getting more and more negative, or negative infinity. So basically we shade everything to the left because x represents all the possible x's, which happen to be, like if it goes negative infinity and it keeps going on, we know that negative infinity is less than 3. Okay? The other way you can think about this inequality, as long as x is on the left-hand side, you can see that the inequality acts like an arrow, but that only works when your variable is on the left-hand side. I call that the arrow inequality trick. And then number 2, this time our boundary number is -1. We still use an open point because there's the strictly greater than sign. The difference is x is greater than or equal to -1. So you could think of it a couple ways. The greater than sign fits around the arrow going to positive infinity, and if the arrow keeps going on, you can even replace the infinity, positive infinity for x, and say, oh, well, is positive infinity bigger than -1? Well, yeah. Every number going to positive infinity is greater than 1, so we're going to shade to the right. The other way, like I said, there's an arrow inequality trick. As long as the variable's on the left-hand side, you see that the arrow is pointing to the right, so that's why we're shading to the right. Again, that only works as long as the variable's on the left-hand side. Now, we use a solid point. I know some people call it closed, for less than or equal to and greater than or equal to. Because of the or equal to, it's going to equal the boundary point. Whereas if it's strictly less than or strictly greater than, like 1 and 2, it cannot equal, x cannot equal the boundary point, or whatever the variable is. So like in number 3, the boundary point is 4, but this time we're going to use a solid boundary point because x can be greater than or equal to 4, so 4 works. And notice with the arrow inequality trick, as long as the variable's on the left-hand side, is pointing to everything going to the right. Or you can even think of it as positive infinity is greater than or equal to 4. In other words, any number going towards positive infinity, I could replace for x and make this a true statement. So like number 4, this time the boundary number is -6. Because of the or equal to, I'm going to use a solid point. And if I use the arrow inequality trick, it's pointing to the left, or you can think of it as, okay, anything going to negative infinity, I could replace with x. Negative infinity is less than or equal to -6. Well, yes. Okay, number 5, so the shaded area represents the x values, or the unknown variables. First thing I look at is whether or not there's an or equal to. Well, there's not, because it's an open point. And we always keep the variable on the left-hand side, and since it's pointing to the negative infinity or getting less than, I'm going to say x is less than the boundary number, which is 13. Okay, number 6, notice that it's a solid point on the boundary number, so I'm going to use an or equal to sign. And because it's pointing to everything going to the right, it's going to be greater than or equal to the boundary number, which is 7. Okay, the boundary number is always where the graph starts or ends. Number 7, we have a solid point, and the boundary number is -18. But notice it's pointing to the left, which is a less than. So I'm going to use x is less than or equal to, again, the or equal to is because of the solid point, to -18. Number 8, we have an open boundary point, but it's pointing to the right, so I'm going to say x is greater than 10. And because it's an open point, I just leave it strictly greater than. Now, rules for solving inequalities. Okay, this is probably the number one rule that no matter what, Algebra 1, Algebra 2, geometry, pre-calc, anything from here on out, this rule applies. Because you must flip the inequality symbol when you multiply or divide by a negative number. Okay, so basically a little shortcut or a hint, I look to see if there's a negative x or negative coefficient on x, which number 9 and 10, they're positive, so I'm not going to have to flip it. But if you look at number 11, it has a negative coefficient on x, I am going to have to flip it. Same thing with number 12. In fact, you could go through and pre-check to see if you're going to end up flipping just by checking the coefficient on x, as long as all the variables are on the left-hand side. Okay, I can show you like a little example. So why this rule holds true. We know that -3 is less than 5, right? Well, if I hold the properties of equality, and let's say I add 2 to both sides. Okay, well, if I add 2 to both sides, -1 less than 7, that still holds true. Okay, let's say I subtract 8 on both sides. So this gives me -9 is less than -1. Well, that's true because -9 is further away from 0 than -1 is. Now let's say I multiply by 2 on both sides. So then I get -18 is less than -2. Well, that's still true because -18 is further away from 0 and -2 is still closer to 0, so that's why -18 is less than -2. Now let's say I multiply by -3. Okay, well, negative times a negative is positive, and 3 times 18, well, let's see, that's -54. Oh, sorry, no, I just said it. A negative times a negative is positive, so that's 54. Less than, again, a negative times a positive is positive. 2 times 3 is 6. Now, all of a sudden, this is where we come into a danger zone. This is as soon as we multiply by a negative on both sides, this symbol is no longer true. So in fact, what happens is you have to slash it out, and it's proven, well, here, before I erase that, 54 is not less than 6. We know that's false. We know 54 is greater than, so the whole point is, since this is not true, this is why we have to flip the symbol. So if you multiply by negative on both sides, we have to flip the symbol in order for the statement to remain true. But if you add or subtract or multiply by a positive, nothing changes. And I could do the same thing with dividing. I could divide by, I don't know, -2. And if I don't flip it, it's going to be false. Because if I multiply or divide by a negative, I have to flip this. Well, if I use the rule and I flip it, well, -54 divided by 2, positive divided by negative, that's going to be a -27. And then if I flip it, less than 6 divided by -2 is -3. Well, as long as I flip it, it's still true. Okay? So let me show you what I mean. Let's just do the odds, and I'll have you do the evens. So if I subtract 2 on both sides, because you're solving just like you do an equation, because you want to get the variable on the left-hand side all by itself, I'm going to eliminate the positive 2 by adding a -2 to both sides, or you can think of it as subtracting 2. So you have 3x is less than -6. Since you're dividing by a positive, we don't have to flip anything. Remember, we only have to flip it when we multiply or divide by a negative. So we get x is less than -2, okay? So basically, if I just label this -2, I'm going to say that's my boundary point. And because it's less than, I use an open boundary point. And x is less than, so I'm going to go to the left. Another way you can use that arrow inequality trick as long as the variable's on the left side. Remember, we read from left to right. So if you keep the variable on the left, the arrow matches with which direction you need to shade. Okay. Now number 11. I was looking at the coefficient. Well, first, I need to undo the adding and subtracting, so we subtract 8 on both sides. Okay. And you've got negative 7x is less than or equal to negative 7. Now, as soon as I divide by that negative, this symbol is false. That's why we slash it out, okay? And you have to flip it. So then x is going to be greater than or equal to positive 1. If we did not flip it, it would be false. So I can put a positive 1 on my number line because it's an or equal to. I'm going to put a solid point. And again, you can use the arrow inequality trick as long as your variable's on the left side and you shade to the right. Okay. Now look at number 13. This time, the x term is second. Now that doesn't matter. We still need to get rid of the constant term first. So if you look at that 3, we're going to subtract 3 on both sides, because a positive 3 is eliminated with a negative 3. So those eliminate. So I have x over 7 is greater than or equal to negative 2. And remember, we do not need to flip the inequality symbol if you're subtracting 3 on both sides. Now, I know a lot of people start to get nervous or freak out when they see a fraction. And remember, fractions are just division. So if I have x over 7, that means x divided by 7. Well, when you're solving, you always want to undo the operation that's currently there, or basically cancel it out. So the opposite of dividing by 7 is I'm going to multiply by 7 on both sides. Now on this side, I'm going to put it as a fraction over 1, because we know a whole number times a fraction, we just make it a fraction over 1. And then I can actually divide out the numerator and denominator, so I get a 1x. 7 divided by 7 is 1x, or just x, is greater than or equal to, well, negative 2 times 7 is negative 14. And I do not need to flip it because the coefficient of x, which was dividing by 7, is positive. Okay? Up here, the coefficient of x was negative, so we had to divide by a negative. Because remember, when you multiply or divide, you do the opposite. But let's back up. If you subtract on both sides, it does not affect the inequality symbol. So anytime you subtract or add on both sides, the inequality symbol stays the same, okay? So if you look at number 15, I know I need to get rid of the positive 3, okay? And I know, just noticing looking ahead, negative 4x, the negative 4 is the coefficient on x. I know I'm going to end up flipping the inequality by the end of the problem. But let's first worry about getting rid of this 3. So we need a negative 3 to eliminate that positive 3. But don't forget to bring that negative 4x down. Don't lose your negative. And then 31 minus 3 is 28. Now, again, just thinking ahead, I'm going to have to divide by negative 4. So I know as soon as I divide by that negative, I'm going to slash out that inequality to remind me that I have to flip it in order for the inequality to stay true, because negatives always change signs, including the inequality signs. And then a positive divided by negative is negative. So here's my boundary number is negative 7. I put an open boundary point, and because my variable's on the left side, it's pointing to the right. Okay. Now look at number 17. Again, I notice the coefficient, which is a negative fraction, tells me by the end of the problem I'm going to have to flip the inequality. But let's not worry about that right now. Let's just eliminate the minus 1. So we have to add 1 to both sides. So we get negative 5/6 x is greater than or equal to 15. Okay. Now, there's a quick way to get rid of fractions. Again, I know a lot of people get nervous about fractions, but basically just think I multiply by the reciprocal. So the reciprocal, you just flip the numerator and denominator, And then if you notice, a negative times a negative becomes a positive, and all the numerators and denominators divide out, so I get a 1x, or a positive 1x, okay? So then I get positive x. I have to flip the inequality because it was a negative, right? We had a negative coefficient on x, so I had to multiply by a negative on both sides. But over here, now let me just write down the flipped inequality. Now let's tackle 15 times negative 6/5. Well, again, anytime you have a whole number times a fraction, you put the whole number over 1. We could multiply straight across, but frankly, I would prefer to do the division first, since 5 goes into 15 evenly, and smaller numbers are easier to multiply rather than if I multiplied 15 times negative 6, I get kind of a big number and then divide by 5. Sure, you can use a calculator, but it's always faster to find these tricks. So if 5 goes into 15 3 times and then multiply by negative 6, you get negative 18. So again, I just write my boundary number. Because it's an or equal to, we know we have to have a solid boundary point. And again, because the variable is on the left side, I can use the inequality like an arrow, and it's pointing to the right. Okay. Now number 19, again, looking ahead, I can tell we have a negative x coefficient. So by the end of the problem, we're going to end up dividing by a negative on both sides, and we'll have to flip it. That's just thinking ahead. But let's just start. We know we have to get rid of the positive 6, so let's subtract 6 on both sides. Okay, so we have negative x. I'm just going to write it as negative 1x to remind everybody that that negative in front of the x means a negative 1. We do not have to flip the inequality because subtracting has no bearing on changing signs. Only multiplying or dividing by a negative do signs change. So 14 minus 6 is 8. So I have to divide by negative 1, which automatically flips the inequality so that it remains true, and you get x is greater than or equal to negative 8. Okay, because again, the negative 1 divided by negative 1 is positive x. We had to flip the sign, and positive 8 divided by negative 1 is negative 8. So then we go ahead, our boundary number is negative 8. We have a solid point because of the or equal to, and since our variable is on the left side, it's pointing to the right, and there we shade it. Go ahead and do the even problems. So pause this video, and then I want you to check the answer key at the end of the video and bring any questions for clarification in class.